In the last class, we discussed the Ket space. Okay, it's a complex vector space. We called it as Ket space. In this class, we'll discuss Bras space and inner products. We are already familiar with the concept of inner products. All right, so let's just revise these things from the usual Euclidean vector space. In the case of Euclidean vector space, we write A vector is equal to, we can write it as a linear combination of three base vectors. All right, we usually write it as ax x hat plus ay y hat plus az z hat. All right, now we also have a scalar product. In the case of Euclidean vector space, we also have a scalar product defined. We are familiar with this. All right, this is how we find the length of the vector, for instance. Okay. So if you have another vector, b vector, let's say it's equal to bx x hat plus by y hat plus bz z hat. In this case, we define a scalar product a vector dot b vector, right? A scalar product or inner product of two vectors. So a vector dot b vector will be ax bx plus ay by plus az bz. Right? So this is the case of Euclidean vector space, and in this case, the vector itself can be represented as, okay, we can represent a vector in a particular coordinate system, right? So I have chosen the base vectors here. I have chosen the coordinate system. In that case, I can represent the vector simply by giving these components along all these three directions. All right. So in this case, we can write it as a column vector, ax, ay, az. All right. So we can represent it by writing it as a column vector. Similarly, we can represent b vector like that. That is bx, by, bz. All right. So this symbol means that I am representing the vector. Right. It's not the full vector. I'm just representing the vector. I'm just representing the vector by choosing a particular coordinate system. So these components depend on our choice of coordinate system. Okay. All right. Now, actually, we cannot combine this a vector dot b vector directly. All right. Actually, we need a dual vector. In fact, we need a dual vector. But in the case of this Euclidean vector space, this dual vector thing we don't emphasize much because the components of the dual vector are the same as the components of a vector. Right? So actually, if we want to construct this a vector dot b vector, it's clear that from here we have to do something like this. All right? It is, we should write it as, let's say, okay, ax. So we could write it like this: ax, ay, az. Okay, this is a row vector, and then the column vector bx, by, bz. All right. Now this would give, this multiplication would give ax bx plus ay by plus az bz. All right. So these things, all right, these we could consider as a representation of a dual vector, a vector dual to the a vector. All right. So it could be a dual vector of a vector. Okay. So these could be considered as the components of a dual vector. All right. The components of the vector we have denoted using a column matrix or a column vector. In this, the dual vector, the components of a dual vector or the dual vector itself is represented in the same basis by a row vector. This is actually a row matrix. All right. This is actually a row matrix. So we see that there is a subtle distinction between this vector and the dual vector. All right. The vector itself is represented by, the vector is represented by a column matrix ax, ay, az, whereas the corresponding, all right, let's say there's a dual vector to that, it can be represented by a row matrix ax, ay, az. All right. So normally these components are the same, and then we don't denote the vector and the dual vector separately. All right. We just define the scalar product like that. Okay. A vector dot b vector is equal to ax bx plus ay by plus az bz. All right. But actually, we cannot combine two vectors as such. We need something else. We need a dual vector space to form a scalar from two vectors. All right. So you could consider this dual vector as a map from the space of vectors to the space of real numbers. In the case of Euclidean vector space, you could consider the dual vector. You could think of the dual vector as a map from vectors to numbers. Okay, it's a map from vectors to numbers. All right, so we cannot really combine two vectors as such directly. We need to find the corresponding dual space. Only then we can map from the space of vectors to the space of numbers. Okay. All right. Now, in the case of, we have also discussed the Minkowski space. In that case, this distinction was clearer. All right. Over there, we defined the scalar product like this. We defined four vectors. In the case of Minkowski space and four vectors. All right. We have already seen this. That's why I'm giving this as an example. We had four vectors. Right? We denoted simply as A, B, etc. There also we had a scalar product A dot B. Okay, there we actually distinguished the components of a vector and of dual vector. Right, this we denoted, for example, as A mu, B mu, one with the lower index and one with the upper index. All right, now these are the components of a dual vector. Components of a dual vector. Okay, these are components of a vector. Right, so this is the convention we used. The upper index was used for vectors and the lower index was used to denote the components of a dual vector. Right, so this lives in a different space. This lives in a different space. Okay, so we could write this components A mu, for example. So a has components vector has components denoted with an upper index A mu, and this had components A0, A1, A2, A3. Actually, you could write it as a column matrix. A0, A1, A2, A3. Okay, these are the components of the four vector. All right, we know how to find the components of the corresponding dual vector. Right, so we used the metric tensor to go from the components of vectors to the components of the corresponding dual vectors. Right, so we had these definitions, and the components of the dual vector we can denote as A mu. Okay, so this we can write this A mu. The components of A mu are actually A0 minus A0, A1, A2, A3. Right, so you could actually write the components of the dual vector as a row matrix and the components of the vectors as a column matrix. All right, but here we see that there is a distinction between the components of the vector and the components of the corresponding dual vector. Right, you see that there's a distinction here. It's A0, A1, A2, A3. In this case, all right, you see that the corresponding dual vector has an extra minus sign for the time component or the zeroth component. Right, so these things we have discussed. So I wanted to revise these things a little bit. Okay, now what we are going to do is that we have discussed this Euclidean space, Minkowski space. All right, now we are talking about a complex vector space which we called as a Ket space. Okay, now we need to define an inner product in the case of Ket space also. Okay, so in this case also we need to define an inner product, and in order to define an inner product you need a dual vector space. All right, you need a dual vector space or a dual space. Okay, so this is what we'll be discussing here, and we'll define the dual vector space, and then we'll define how inner products can be formed. Okay, so this is what we'll be doing in this session. The vector space that we have been dealing with so far was called the Ket space. Once we have set up a vector space, we can define another associated vector space of equal dimension known as the dual vector space. As I said, this is true in the case of all the vector space that we have studied so far. Okay, if it's a Euclidean vector space, over there also we are actually defining a dual vector space. In the case of Minkowski or four vectors, also we were constructing a dual vector space. All right, the aim of the dual vector space, the aim of thinking about the dual vector space mainly is as a map from the space of vectors to a space of numbers. All right. Okay, so we now introduce the notion of a Bras space, a vector space dual to the Ket space. So space of vectors we call the Ket space. Okay, the dual space, the dual vector space of the same dimensionality as the Ket space, it's called a Bras space. So the idea of the Dirac's idea for coining these terms was, when you combine a Bra and Ket, you get a bracket. Okay, we get a bracket. All right, there's a semist there, so we could write a C there if you want, but generally you can think of this as a bracket, and a bracket is a number. All right, it's a number. Okay, Ket is a vector, bra is the dual vector, bracket is a number. So bracket stands for a scalar product or an inner product. Okay, we'll mostly use the word inner product. Maybe from earlier we would have been familiar with the term scalar product, but in this textbook they have used the word scalar for a specific kind of numbers, all right, so a specific kind of objects, all right, so we'll call it inner product, we'll call it as inner product. Okay, now we postulate, the idea is that we postulate that corresponding to every ket alpha, there exists a bra. Alright, so just like we said that corresponding to every vector, you can construct a dual vector. In the case of Minkowski space, alright, we know how to go from the components of the vector to the components of a dual vector. Alright, in the same way, we postulate that corresponding to every ket, there exists a bra. Okay, and we'll denote it simply in this manner. Okay, we'll denote it simply in this manner. So a vector was denoted like this. Dual vector will be denoted, or the corresponding dual vector will be denoted like this. All right, you see that the angle is to the opposite direction. All right. Now we said that okay, if we are talking about an operator A, if we are talking about this particular observable, then we will have to use a vector space whose dimensionality is equal to a number of possible different measurement outcomes. Right? So the dimensionality was equal to the number of possible measurement outcomes, or the dimensionality was equal to the number of eigenvalues for this particular observable or operator. We have discussed these things, and we said that the space is spanned by the eigenvectors. Okay, the space is spanned by eigenvectors of operator A. All right, this we have already discussed. By spanning, we mean that any vector can be expanded. Okay, any vector can be expanded as a combination of these eigenvector. All right, eigenvectors. So if you have the set of all eigenvectors, we can consider them as a base set. Right? We haven't proven any of these yet, but we'll be discussing the details later on. So basically, we are talking about a complex vector space spanned by the eigenvectors of the observable under consideration. Okay. All right. Now we said that corresponding to every, we postulated that corresponding to every ket there's a bra. Okay. There's a bra. All right. And this bra space can be considered as, because to corresponding to every ket there's a bra, corresponding to every eigen ket there is an eigen bra also. All right. So these kets, the corresponding eigen bras can be written like that. Okay. Bra A prime. All right. So we can say that this space, the ket space, is spanned by the eigenvectors, the set of eigenvectors denoted as ket A prime, or ket A double prime, etc. We said that we'll denote the set like that. All right. Now the space of the dual vector space, or the dual vector space, can be thought of as being spanned by the eigen bras instead of the eigen kets. Okay. We are allowed to do this because we have postulated that corresponding to every ket there is a bra. So corresponding to this ket, there is a bra. Corresponding to each of these kets also, there is a bra. All right. So we can think of the bra space as being spanned by the eigen bras. All right. So this set means that this is the set of all the eigen bras, A prime, A double prime, etc. Okay. A triple prime goes on like that, right? Which correspond to the eigen ket set, correspond to eigen ket given by this set, right? A prime, A double prime, etc. So this was a shorthand notation for the set of all the eigen kets of the operator A. All right. Okay. Now the idea is that there's a one-to-one correspondence between a ket space and a bra space, which means that one-to-one correspondence means that corresponding to every ket there is a single bra. All right. Corresponding to every ket there is a bra. So this is a one-to-one correspondence. So corresponding to one ket there is one bra. This is called a one-to-one correspondence. All right. So we can denote it like this: corresponding to every ket alpha, there's a dual correspondence. All right. This DC stands for a dual correspondence. The dual correspondence is denoted as corresponding to every ket, there is a bra which is denoted like this. All right. So if you have the set of eigenkets, all right. So to each of these kets, there is a corresponding bra. All right. So corresponding to a set of eigenkets, you have got a set of eigenbras. All right. This is a set of eigenbras. This is a one-to-one correspondence. Okay. Similarly, we know that if you take two kets and add them, you get another ket. All right. We have already seen this. So corresponding to this also, there is a bra. Okay, we know that alpha plus beta is another ket. We can call it as gamma. So corresponding to gamma also, there is another bra, which we can write it as bra gamma. All right, and the corresponding bra is written like this. It's bra alpha plus bra beta. So we take each of these vectors or each of these kets and take the corresponding bras. All right, that will give you bra gamma. All right. So DC is the short form for dual correspondence. All right. Now we can regard the bra space as some kind of mirror image of the ket space. All right. You could think of the bra space as some kind of mirror image of the ket space. All right. Now the bra dual to C alpha. So if you have got something like vector multiplied by a complex number or a vector multiplied by a scalar, okay, the corresponding bra is denoted as C star bra alpha and not simply C bra alpha. It is C star bra alpha, right? So when you go from a space of kets to a space of bras, the complex numbers, right, the numbers will pick up an extra complex conjugation. The numbers will pick up an extra complex conjugation, right? This is how we define our bra space, all right? Now, in our context of quantum mechanics, the reason for this definition will become clear soon. All right. So the bra dual to C alpha is postulated to be C star bra alpha, not C bra alpha. Okay, this is very important. Right? This is very, very important. The idea is that complex numbers have a fundamental role in quantum mechanics. Okay, and these complex numbers can be related to certain probabilities, and we need these probabilities to be real numbers. We need these probabilities to be real numbers. Okay, so that's the reason why one way to construct a complex number out of a real number out of a complex number is to multiply it with its own complex conjugate. All right, so if you take C star, you can write this as modulus of C square. This is a number, this is a real number, a positive definite number. Okay, this is a real, let's say this is a positive definite number. All right, now we'll see that this is the reason why we, at least in the context of quantum mechanics, this is the reason why we need to postulate that the bra corresponding to C ket alpha is C star bra alpha. So we'll see this when we discuss an example. All right? We'll see the importance when we discuss an example. So we could write this more generally. All right, C alpha, this is some expansion coefficient ket alpha plus C beta ket beta. Okay, this is simply a combination of two kets. This is simply a combination of two kets or a linear combination of two kets, which is another ket, obviously, which is another ket. The dual correspondence to this is given by C alpha star bra alpha plus C beta star bra beta. Okay, for now you think of it as a definition of our bra space. All right. Now we can define the inner product of a bra and a ket. The product is written as a bra standing on the left and a ket standing on the right. Okay? So we could define a bracket. Okay? If you have a bra alpha and ket beta, we can simply combine them and call it a bracket. Right? We'll call this as a bracket. Okay? We could simply write it as bracket. So basically Dirac took this word bracket and divided it into two. One part he used for the dual space and the other part he used for the vector space. All right. Okay. So this is how we denote an inner product in Dirac notation. Okay. So this means that we are combining a bra with a ket. We have formed a bracket, and this will be a complex number. This will be a complex number in general. This will be a complex number. All right. Because the scalars that we are talking about in this complex vector space, these scalars could be complex numbers, right? We already said that we could combine vectors by multiplying them with complex numbers and add in, right? That's what we have done here. We have taken two vectors alpha and beta. We have multiplied them. We are allowed to multiply them with complex numbers, okay, because we are dealing with a complex vector space. All right. Now this product is in general a complex number. Notice that in forming the inner product, we always take one vector from the Bras space and one vector from the Ket space. Right? So we cannot form an inner product between two vectors from the same space. Right? We cannot form an inner product between two vectors from the same space. All right? In order to form an inner product, you need to take one from the dual space and the other one from the one from the Bras space and one from the Ket space. Okay? You cannot combine vectors from the same space. You need the dual space. All right? So you could think of this Bra alpha as a map, as a function that takes alpha to a complex number. Right? In this case, this is a complex number. All right? So you could think of this as a map or as a function that takes the vectors to a complex, takes the vector Ket alpha to a complex number. Right? So you could think of this as some sort of a map that takes that takes a vector as an input and spits out a number, Okay, that's what roughly what we mean by a map. Now we need to postulate two fundamental properties of inner products. Okay, the first thing that we postulate is that bracket beta alpha is equal to bracket alpha beta star. So that means that if you change the position of alpha and beta, if you interchange the position of alpha and beta, you get a complex conjugate. All right. So we know that beta alpha, a bracket, it's a complex number. All right. And then alpha beta, bracket alpha beta, will also be a complex number, but it will be the complex conjugate of the first one. It won't be equal to the first number. All right. So when you interchange this alpha and beta, you get an extra complex conjugation. So bracket beta alpha and bracket alpha beta are complex conjugates of each other. All right. Now we already talked about the analogy with the scalar product that we are familiar with from the Euclidean vector space. All right. For example, we said that this is similar. The scalar product here is similar to the scalar product like this a vector dot b vector. Right. So this was equal to ax bx plus ay by plus az bz. Okay. Now, if you want to represent it using matrices, column matrices and row matrices, we could write this as ax, ay, az and bx, by, bz. All right. Now, this we said you could think of this as the components or the representation of the vector in the dual space. Okay. So you have got a vector space and a dual vector space. All right. So we need a dual vector space in order to combine to construct a scalar, a number. All right. So this would give ax bx plus ay by plus az bz. All right. Now we could write the same thing as we could take the dual vector corresponding to b vector and do the same thing. All right. We could simply write this as bx by bz ax ay az. All right. And again, you will get the same thing ax bx plus ay by plus az bz. We get the same thing. All right. So or we can say that a vector dot b vector is equal to b vector dot a vector. All right. It doesn't matter whether a vector comes first and then b vector after, or b vector comes first and then a vector. The scalar product, the inner product, is the same in both cases. All right. But that's not the case in the case of for us. That's not the case for us in the complex vector space that we are dealing with. We define the inner product like this. All right. Bracket beta alpha is equal to bracket alpha beta star. Okay. Bracket beta alpha must be clearly distinguished from bracket alpha beta. All right. The analogous distinction is not needed in real vector space because a vector dot b vector is equal to b vector dot a vector. All right. Now using this, we can immediately deduce that bracket alpha alpha. Okay, you can think of this as the scalar product with itself. All right, or the inner product with itself in some sense. All right, so bracket alpha alpha must be a real number. Okay, this we can easily check. Bracket alpha alpha has to be equal to bracket alpha alpha star. Okay, according to this equation, right? So you have got a number here, which is the complex conjugate of itself, right? So this means that it's a real number. If you take the complex conjugate of a real number, you get the same number, right? So this is real. So bracket alpha alpha is a real number, all right? So the inner product between ket alpha and the corresponding bra, all right? If you want to be really precise, we shouldn't really think of it, we shouldn't really call it the inner product between two vectors. It's actually an inner product between a vector and the corresponding covector or the corresponding bra, okay? The inner product between a ket and the corresponding bra, all right? So that's the first postulate that we'll need. We will see that this is important for the probabilistic formulation of quantum mechanics. The second postulate on inner products is that bracket alpha alpha is greater than or equal to 0. Okay. So the equality sign holds only if ket alpha is a null ket. If it's a null ket, then this will be equal to 0. Otherwise, it's greater than 0, which means that it's positive. Okay. So the inner product between ket and the corresponding bra, we postulate that it has to be positive. And this is also important in the probabilistic formulation of quantum mechanics, as we'll be seeing soon. Now, this is sometimes known as the postulate of positive definite metric. So we say that the metric is positive definite, right? And I think we are already familiar with a positive definite metric. If you have a vector dot a vector, we know that it is greater than or equal to 0 in the case of Euclidean vector space. This we already know because this is ax square plus ay square plus az square. So if all the components are not equal to 0, this is clearly positive because it's a sum of squares. All right. Now we are also familiar with metric that is not positive definite. Right? For example, we have studied the Minkowski metric. In that case, the inner product could be positive, negative, or 0. Right? In that case, the inner product of a vector with itself. Okay, this could be positive, negative, or 0. Okay, I think this is one way to write that. All right, it's positive, negative, or 0. So in this case, the Minkowski metric is not positive definite, but in quantum mechanics, we postulate that it is actually positive definite. So we are talking about a positive definite metric. Now, from a physicist's point of view, this postulate is essential for the probabilistic interpretation of quantum mechanics. Right now, this will become clear later. We'll be discussing an example of all these concepts after this session, in the next session, and then these things will try to discuss all these things. All right, how all these things come up and how all these things are important in quantum mechanics. Now, another important property. Another important definition is that of orthogonal vectors. Right? So we know that in the case of usual Euclidean vectors, we can define orthogonality like this. So let's talk about these unit vectors which are perpendicular to each other. In this case, we know that x dot y is equal to 0. Right? X dot y is equal to 0 and y dot x equal to 0. Now we know that the meaning of this is that y hat, the unit vector y hat, does not have any component in the x direction. Y hat has no component in the x direction. All right, or in other words, x hat has no component in the y direction. So if you expand x hat in terms of some other vectors, it will never involve a y hat. That's what it means. All right. So in this case, all right, in the case of Euclidean vector space, orthogonal also means they are perpendicular. Okay, orthogonal also means that they are perpendicular, but that need not be the case. All right. So in general, orthogonality, we say that two vectors are orthogonal if their inner product is equal to 0. Okay. So in the special case of the three-dimensional Euclidean space, this also means that they are perpendicular, but orthogonal itself, it's a more general term. So we say that ket alpha and ket beta are orthogonal if bracket alpha beta is equal to 0. Okay. Now, even though in definition the inner product of in the definition the inner product bra alpha appears. All right. So we say that two kets are said to be orthogonal. So if the condition for orthogonality involves changing one of them into a bra. All right. This actually we also do here, but we don't notice it, right? Because the components do not change, etc. We don't notice it. All right. So if the scalar product, the inner product of two vectors, we can think of this as we can call this, all right, as inner product of two vectors. But actually, you have to remember that it's an inner product of a vector and a dual vector, or inner product of a ket and a bra. Okay, it's a bracket. So these vectors are said to be orthogonal if bracket alpha beta is equal to 0. Right? It's important to remember this. Right? Now, if bracket alpha beta is equal to 0, then bracket beta alpha also will be equal to 0, because we know that bracket beta alpha is equal to bracket alpha beta star. So if this is equal to 0, right, if bracket beta alpha is equal to 0, 0 is the complex conjugate of 0 itself. All right. So if bracket alpha beta is 0, this also means that bracket beta alpha is 0. All right. So if you are checking for orthogonality, it doesn't matter in which order you combine beta and alpha. All right. You could either combine bra alpha with ket beta, or you could combine bra beta with ket alpha. Right. And if they are orthogonal, both these would be equal to 0. Right. So bracket beta alpha has also to be equal to 0 if they are orthogonal. Now, given a ket which is not a null ket, we can form a normalized ket alpha tilde. Right? Suppose bracket alpha with itself, right? Bracket alpha alpha is not equal to 1. Right? Suppose bracket alpha alpha is not equal to 1. Okay. Now we can use the freedom, because we already said that if alpha represents a physical state, then any multiple of alpha also represents the same physical state. Okay, so you could multiply this vector or this ket by a number without changing the state that the vector represents. So we have this freedom to do this in quantum mechanics. Right? Now it is very convenient. One reason is that it's convenient to choose these as unit vectors. Right? It's better to use this as unit vectors. We'll see that it is important when we talk about probabilities also. All right. Now, since it doesn't matter, the state you represent does not change if you multiply a ket by a number, we can just multiply the ket by a number and make sure that the inner product with itself is equal to 1. All right. This process is called as normalization. This is called normalization. All right. Now, suppose bracket alpha alpha is not equal to 1. All right. Then we know that this is a number. We know that this is a real positive number based on the postulates that we had. All right. So this is a real positive number in this case. In general, in general, a scalar product of two vectors, or the inner product of a bra and a ket, could be a complex number. Right? But we already defined that. We already showed that based on the postulates, this is both real and positive. Right? Anyway, so if bracket alpha alpha is not equal to 1, then we could define another vector alpha tilde, okay, which is a multiple of alpha. All right, so you multiply this by 1 by square root of bracket alpha alpha. Okay, now the reason for us to do this is that if you do this, then bracket alpha tilde will be equal to 1. Okay, now we can check this if you want. Just to be sure, let's write bracket alpha tilde is equal to, since this is a real number, a real positive number, all right, we can write this as 1 by square root of alpha alpha. Actually, you need a star here, right? We know that when a complex number goes to a dual space, there's a complex conjugation that follows. All right, so we already said this, that if you have a vector C alpha, the bra corresponding to that is C star bra alpha, not C bra alpha. Okay, so you need a star here, but since this is real and positive, we don't worry about that now. Right? So this is bra alpha tilde is equal to 1 by square root of bracket alpha alpha and then bra alpha. Okay. Now ket alpha tilde is already here. So let's do this combination. Bra alpha tilde multiplied by the product of bra alpha tilde and ket alpha tilde. Okay. So this you can write as, let's write this together. This is 1 by We write it here. So this you could write as 1 by square root of alpha alpha bra alpha tilde, sorry, bra alpha, okay, bra alpha multiplied by, so this is our bra alpha tilde, okay, multiplied by, we've got 1 by square root of bracket alpha alpha and then ket alpha. What is this? This is ket alpha tilde, right? So that's how we define the ket alpha tilde here, right? Okay. Now, since these are numbers, 1 by square root of bracket alpha alpha and 1 by square root of bracket alpha alpha numbers, it doesn't matter whether we put it on the right side of the bra or on the left side of the bra. It doesn't matter. Okay, so we can just bring these together. So if you multiply these together, it becomes 1 by bracket alpha alpha. Right, now you can combine this bra with this ket. You can combine this bra with this ket, and then you have got bracket alpha alpha. Okay, so on the numerator and denominator, you have got the same number, which means that this is equal to 1. All right. Now, this process is called normalization. Right. So we say that the ket alpha tilde is normalized. We say that the ket alpha tilde is actually normalized. Okay. Now, quite generally, square root of bracket alpha alpha is known as the norm of ket alpha. Okay. This is called the norm of ket alpha. Now, this is analogous to the magnitude of a vector. So, in the case of Euclidean vector space, we have got a vector dot a vector, right? A vector dot a vector, we call it the what is square root of a vector dot a vector. We say it's the magnitude of the vector, or we say that this is the length of the vector. All right, so we write this as, this is actually, we also denote it as modulus of a vector. Right? This is the magnitude or length of the vector. In the same way, right, this is something analogous. This you could think of as the length of the vector. You could call it the length of the vector. All right. So what are we doing here is that in quantum mechanics, since we are allowed to multiply the vector by numbers without changing the state it represents. All right. So it's convenient. So we can use this freedom to choose all unit vectors to represent the quantum mechanical states. All right. So what we are doing here is that we are choosing unit vectors to represent quantum mechanical states. Okay, that's what we have done. So this is convenient. Now, because ket alpha and C ket alpha represent the same physical state, we might as well require that the kets we use for physical states be normalized in the sense of this equation. All right. So essentially, we say that we are going to use unit vectors in some sense. All right, we are going to use unit vectors to represent a quantum mechanical state. All right, now if the given state, if the given vector is not a unit vector, then we'll make it a unit vector by normalizing it, by multiplying it with the number. Right, here we have multiplied ket alpha using by a number to make it normalized. Right, so this normalization is important again in the case of the probabilistic interpretation of quantum mechanics. Right. Now we have said all these things. I'll in the next session we'll discuss an example, right, where all these properties and postulates are made use of, right, and I'll try to explain in that example how these postulates are important for a probabilistic interpretation, why these are important for a probabilistic interpretation. So let's discuss an example next.